It's my pleasure to introduce John Smith from the IBM Watson Research Center. He's a Columbia PhD who's been working on video indexing, retrieval, sorting. He's a lead author of the MPEG7 Standard for video metadata markup. In 2003, he won the Multimedia Prize for Best Paper over the previous 4 years from the IEEE. He's an IEEE fellow. He's here today talking to us because he's giving an all-day presentation tomorrow. Well, he's in an all-day meeting tomorrow with the IEEE committee. He currently leads IBM's multimedia analysis and retrieval research area, and he's going to talk to us today about how he's been devising technologies and using them to improve video search. So I'm sure it'll be very helpful and interesting for us. Thanks, John.
Thank you, Jeffrey, for the introduction, and it's really my pleasure to be here. This is my first time to Google, and I've been here all of about an hour, and I must say it's pretty impressive. And when I first was driving up and I saw all of these bicycles and so on, I thought, oh, that's really novel. I wonder why they're needed. Until I needed to get a parking place, and then I realized what the bicycles were really for. But it's really my pleasure to be here. So today I want to talk about some of the work that we've been doing and that has been going on in the research community around video search. And so I'll talk about some of the challenges with video search right now. And there are many ways in which video search can be improved. And some of the key ideas have to do with trying to get a better understanding of the contents of video, modeling the semantics, and so on. So I want to talk about some of the work that we've been doing that we published recently at some conferences and so on. And I want to talk about some of the community efforts that are also going on now around video search, having to do with public evaluations and efforts to create ontologies for multimedia as well. And I want to show how this connects also to efforts like the MPEG7 Standard, which is really quite different from the previous MPEG standards. MPEG7 is all about how do you describe multimedia content in a standard, and in this case, XML representation. I have some demos and so on that I'm going to show throughout. I think if you have any questions at any point, though, please feel free to ask. So let me just start a little bit up front to motivate the problem, although I'm sure many of us realize that video is rapidly becoming an important medium of content for people to interact with. It's introducing many technical challenges, though, for IT. The relevance is seen in a lot of different industries. It's not just media and entertainment, but traditional enterprises are needing to deal with collaboration assets and conferencing and so on. The challenge with video is that it's not naturally self-describing, whereas with text documents and so on, you have something to go on to build an index and search. Video itself, the pixels don't necessarily tell the whole story. You need metadata to effectively use it, and clearly not enough metadata is being generated. The expectations are clearly increasing around video. This is a chart that was in Wired magazine not too long ago in June, and the whole idea is that, well, video isn't as easy to search as text. Nobody has really figured out the best solution yet, and who will be the next Google for video search? Maybe it will be Google. But to date, there are different approaches that are being taken to make video searchable. Some of them are typified in search engines like Blinks, which rely solely on the speech portion of the video content. They try to do some very clever things to find keywords and terms and so on from the speech. But even with all of that smarts, speech is not a very good descriptor of what's in the video. And it certainly doesn't tell you what's being shown on the screen. A completely different type of approach has to do with trying to leverage information in web pages, so scraping text and so on. And there are search engines like searchvideo.com. This is AOL's Truvio search engine, which does just that. But that also has some limitations. The really interesting approach, and what I'll talk about today, is trying to leverage computers to better understand the content visually and try to improve search that way. And Wired characterized this as still being a tech that's stuck in the lab, but I think that it's also poised to make a real impact. So coming back to this idea about metadata, all video search relies on metadata in one form or another, whether it comes from being manually authored or from speech transcripts or scraped or so on. But today's metadata is not good enough. There are a number of dimensions in which it falls short. There's not enough of it. When it's there, it's inadequate. Often the tags and so on that get created describe whole item levels. They don't go in and say, well, what's happening in individual scenes within a video, which might, of course, be interesting for users and for other purposes. It's not visual. There's a lot of ambiguity because taxonomies are not standardized. Folksonomies are interesting, but they create problems of their own. Standards like MPEG7 can give us a way to represent controlled vocabularies and so on in a standardized way. So the mechanisms are there. They just need to be put in more widestream practice. So there are a bunch of issues where metadata is falling short. And there are different needs depending where you are in the spectrum with digital objects themselves. Of course, there are always going to be some area of content which is your really popular content. These can be your hit TV shows and so on, that there will be a role for manual professional cataloging of that content to create episode guides and put transcripts out and all of those kinds of things. And this is indeed happening today. Interestingly, at the far other end of the spectrum here, so this is a plot of, let's say, the popularity of digital items. Consumer content, and with sites like Flickr and so on, are leveraging the digital masses to do work, to create tags and so on. But these are really just extremes of the overall spectrum of the digital objects that are out there. This is a tail which is very long. There are deep archives which aren't really being exploited. There's raw footage related to what is being produced. Think independence and so on. So it's this region here where perhaps there's the most bang for the buck if we can leverage the computers to do work to make this content searchable. The quality may be less than what could happen for the professionally cataloged stuff, but that may be okay if the only other option is to just not exploit it at all. Okay, so a little bit more on where video search is not satisfying. There are studies, one from Emarketer not too long ago, which characterized some dimensions where video search is not working well. And again, typical video search now relies on some simple ways of capturing metadata that may or may not really be reliable later for searching. If you look at some of the search engines that are out there, and in this case, there's a query on each of them for just the term basketball, and we can see the results coming back on Google Video and Brightcove and Blinks and AOL. Well, they're all completely different results. And Blinks, for example, returns 214,000 matches, and there's really little ability for the user to refine or say, well, no, I want a player interview, or I want a game scene, or something like that. And the key dimensions here to think about with video search in this way is the depth at which the user can do a search and the computer can find matches. So how descriptive can the user be in the query to get matches for their search? And breadth. A lot of the search engines today rely on partner content that populates their silos, so they search narrowly, within just a small set of the overall video resources that are out there. So there's really no one engine which has gotten depth and breadth yet mastered. So I'm going to move a little bit now into some of the technical approaches that are possible for this kind of problem, but I want to put it into a little bit of perspective of how research disciplines have evolved, going back a little bit of ways. Some of the earliest work on image content-based retrieval happened in the early mid-1990s. Actually, IBM was one of the pioneers in this area with a system called QBIC, which stands for Query by Image Content, and it was all about extracting descriptors of photographs that could then allow queries where the user could say, well, give me more photographs that look like this one. And it would find things that have similar color or texture, and certainly very interesting technology to play with. And even today, we're still playing with things like that. Problem is, users don't necessarily want to search that way. It might be a nice add-on in a search engine, but other mechanisms are needed to really get that going. But there's certainly a lot of follow-on work around that, which is to try to make the image matching better by characterizing spatial regions and matching of images in smart ways based on layouts and orientations and all of those kinds of things. And that certainly generated a lot of neat ideas, and once people started to be able to handle digital video more routinely on computers, then certainly attention was turned to, well, okay, how could we push also on video? And so then the work there got focused on things like automatically detecting shot breaks in a video and summarizing long video. So let's say you take an hour video and you create a 5-minute summary of the highlights, those kinds of problems. Now, indeed, these are nice building blocks to have, but I think the real interesting work is happening recently, which is to try to take the ability of the computer to analyze features, to process and make sense out of video as a temporal medium, to extract semantics. So in other words, for the computer, going back to our earlier scenario, for the computer to learn what does a basketball game or scene look like, and how is that different from a baseball scene or another kind of sport or any other kind of video that's out there. These are things a computer can learn through training. So we've been doing work in this area at IBM Research. We have a system. It's been out on our IBM AlphaWorks site for download for more than a year now. And the idea there is we create this computer-based machine learning approach, by which the system is taught what different categories of content look like, and then it has the ability to go out, hunt that down, automatically tag and score those kinds of things. And so I'm going to go through some demos in a little bit, but let's look a little bit more at what's behind it. So the idea is with some kind of input video, to try to leverage the computer where it can help a lot in analyzing. And as I described, the ability of the computer to extract features is long established, going back to that early work on image content-based retrieval. MPEG7 has even standardized descriptors for things like color and color histograms and edge histograms and texture descriptors. There's already a very good foundation of things there. The next challenge is, and where we are working, is to go one layer further, which is to create models of semantic content that could use this information. So when we have visual information only, we have a path there, which is to analyze the visual features, build models on those. When there is text information like speech, that can also be useful, but typically you need to consider modes when you don't have any text. But certainly that text information can be leveraged in models as well. And the idea is for a video stream to get some kind of tag stream generated by the computer that goes along with it. And typically there are scores generated for these tags, which are some indication of the confidence level that the computer has when it assigns that tag. And they can be very useful later for searching when you want to rank a result or fusing together and so on. So behind this approach then, since it's a very much a data-driven approach where models get created, is the need to build out taxonomies that are illustrated with example multimedia content. And this is just an example of one of the tools that we're working on, but I think it helps convey the concept, which is for different categories of in a taxonomy, to create a model, all you need to do is load in example images for that category. And it can be, in some cases, as few as 40 examples. In some cases, it can be thousands or even tens of thousands of examples if it's important to get a really full description of that category. Or if it's just a very common category, in some cases, it can be even easy to get that many of examples. So this is really the type of starting point that's taken to create the models. So I'm going to go into now 4 areas of research to make this work, and there are recent publications we have on these, and I'd be happy to give that information if people are interested to follow up. But we're working broadly on this space, which is how to build the models for video content, and that can include not just image scenes on themselves, but even temporal information, like is the scene showing an airplane that's taking off or one that's landing? So you need more than simply an airplane detector. You need to know something about the temporal information. We've been working on also combining supervised and unsupervised classification together. So for example, a computer can not only run models against features, but it can do things like clustering and so on those features as well. And there are some interesting things on how do you fuse the ability to tag along with the ability to cluster. And then these kinds of information generated here then has a role in search, and there are a lot of interesting things. So how do you put it all together in the search engine, which may have other modalities of search that can be supported based on speech and so on. So we're not saying do away with speech. What we're saying is let's enhance it and do a better job as a result. Okay, so I'm going to start on the first problem there, which is in building the models, there are always going to be issues of how do you find trade-offs and how can you make classification really fast or scale to thousands of or even hundreds of thousands of classifiers. And I'm going to talk about something we're doing on this dimension here, which is so one of the techniques that can be very useful for building a classifier is to use something called support vector machines. We can just think of it as producing some kind of decision boundary between your positive examples and the negative examples for your classifier. And it's a very powerful type of machine learning tool, which is good for this space. But there are always issues with support vector machines, and your model files can be very big, needing to scale, and how do you do that? One of the techniques that we recently published at the KDD conference just this summer is based on something called random subspace bagging, and basically we can think of it as, so I mentioned we have features that get extracted from your content. So we can think of those features as being decomposed into dimensions. So let's say we take our color descriptor and our texture and we just stack them side by side. And we get really a high dimensional vector that goes this way. And then on this dimension are our training examples. Here they're called training shots because these came from video. But think of it as, so this row here represents one example video shot, and these are all of its dimensions of its feature descriptors. So typically when you're creating a classifier using something like support vector machines, you use this whole data space. So in other words, you put in all of your features, you put in all of your training, you say here are the positive, here are the negative, and then you learn from that. What we found is through this concept called a random subspace bag, which is you do a random sampling of your feature dimensions in your training examples. So in other words, you create just an extract like this, and then you learn a model based on that. And then you repeat. And what you do is you create an ensemble of these unit models, as we call them, and then we fuse these together. We get a lot of nice properties. These unit models are faster to learn. They're faster to run against your video content later on. The fusion is a very simple fusion because it's just averaging. In other words, by being random, each unit model is no more likely to be good or bad than any other. So you don't have to worry about learning at the fusion step to say, I need to weigh texture more than color and those kinds of things. Here, everything just comes together very well. We did this mainly because we were motivated to scale to a large number of classifiers, but when we ran this kind of learning against real data sets, we discovered that we can not only get the equal performance from learning over the original space, but we even got improvements in the overall classification accuracy. And this has something to do with maybe being more robust to noise or something when we're doing this kind of sampling, but we're still maintaining very good performance in terms of the accuracy of those models by just using these extracts. The real important result, though, is the efficiency gain by just using these random subspace bags, and we can reduce our training time significantly, so up to close to a 60-time speed up. Actually, no, I'm sorry. This is the reduction in training time. So, typically on the order of 60 to 1, 98 minutes to just 100 seconds to learn a full set of models from a training corpus. And this is about 40 models that were learned here, and also on consumer video. And also, again, later in the testing time. So testing is when you're running new video through the system later, and it's using those models to classify the contents. And I'll say a little bit more about the TRECVID data corpus later on. But that's one of the standard test sets that we've been working against. Just one more slide on sort of the efficiency and scale dimension. You can sometimes learn your models ahead of time, like I just showed. If you know that it's really important to have a classifier for basketball scenes, then you do the work up front, you create that classifier, it's ready to go. Maybe you tweak it and improve it over time, but it's done ahead of time. In some cases, maybe a classifier needs to be created on the fly. Maybe there's a new information need, or a user has something in particular in mind. One example was find scenes of a demonstration or protest. Now, maybe you can't anticipate that people will want to look for that thing later. So we've wanted to support, well, how could you rapidly put together a classifier which has few examples? So it becomes an imbalanced learning problem in that you just have a small number of positive examples. It could be 5, it could be as many as 10, but in the relative scheme of things, that's a small number of examples according to our the feature number of dimensions in the feature space. So we worked on a technique, and this was published in the conference on multimedia this summer, which leverages unsupervised classification along with the modeling to say that, well, the computer can figure out where the pockets of similarly appearing visual content appears. And what we do is we take our examples and we just map them to those pockets. And when we get enough hits, we just say, well, let's just use that centroid to represent our positive classes. And we do the same thing for negatives, and then we just learn from these centroids. What we get is extremely rapid way to create a model on the fly. And this happens to also be very efficient model. It doesn't contain a lot of examples, a lot of information in that. It only retains the centroids from these clusters. So that's another work we did along this dimension. Sorry, question, Jeffrey?
The question, it seems like your negative examples are selected to be as similar to a street protest, but not actually a street protest as possible. Is that significant?
There is a concept here which can be very useful. Okay, the question is how negative examples can be chosen. And so there's actually a concept which is very useful here that we call near negatives. So in many cases, you can find negatives that have absolutely nothing to do. Like you could put indoor scenes here, or portraits of faces, or something that's totally unlike protest. So it's important to know what is clearly not an outdoor protest scene, but there's also, it can be very important to have examples which are close to the decision boundary to help the computer be precise where it really matters. And these negative examples weren't meant here to necessarily be near negatives or be close, but we found that in practice that it sometimes is very useful to go through this iteration stage with a user where you create a classifier based on your positive and negative, you run that on some other set, you see what the results are, you give back the users examples that are close to the decision boundary, and then you take that feedback into the system. This whole concept is known as active learning, sort of in the academic community and so on. But you iterate with the computer on giving human judgment input on the examples which the computer is most uncertain about. And those are usually the ones that are closest to the decision boundary, not the ones that are already very far away. So that's certainly a very interesting concept to apply here. Okay, a little bit more on the cluster labeling. Actually, I'll show this one in the demo system. But basically, the idea is that if we have this ability to run classifiers against the content in a repository, we get some labels. We also have the ability to automatically create clusters. Let's bring the two of these together. So in other words, the computer discovers there's a pocket of content that fits into a cluster, and they're like scenes. There's some homogeneity to them in some feature space. So the idea is, well, how do you pick your labels that may or may not be assigned individually to the items in that cluster and aggregate in some way to label the cluster? And the interesting thing here is you don't necessarily want to pick just the dominant label in the cluster. The reason is, typically half of your scenes are outdoors. So it's not very informative to label every cluster as outdoors. What you want to do in many cases is have labels assigned to your cluster which are discriminative. So it says, what is it about that cluster that makes it most different from all of the other clusters? So this is a work we did recently as well. Okay, so I think what I'll do here is I'll go a little bit into the demo system that we have. So a lot of these things are coming together overall in the search engine, including searching, basing over text, including the models and so on. Okay, and then I'll come back to some more details. Okay. The first thing I will show here. So this is a data set which we obtained through our work on the NIST TREC video retrieval benchmark. So it's put out by the National Institute of Standards and Technology each year. It was originally provided to them by the BBC, and these are known as B-rolls to the BBC. Basically, you know, someone goes out into the field somewhere, puts out a camera, they capture something from a scene, and then it just kind of gets dumped back into the organization. There's no metadata, there's no tagging, there's no speech transcription, there's nothing. It's just raw video. So what we've done is we've run this video through our system, and I'm just going to show a few classifiers here that I think really help illustrate what I've been talking about so far in the talk. But we can see it's just, you know, it's a wide variety of content. Each of these is a keyframe selected from some shot in the video. So there's actually, you know, a few second, or it can be, you know, even longer video clip behind each of these keyframes. So after we run some classifiers through it, let me switch to this view. We can see, you know, how it's doing its work. I like to show this one because, well, this is a classifier, well, we just called Greenery. Anyway, it was trained on examples of images that show outdoors greenery type scenes. And often when I show this to people, they say, yeah, the computer's just finding stuff that's green. And it is. That's precisely the point. But there's a little bit more to it than that. And we can see that, yeah, these scenes do have green, but there's a certain textural characteristic to them. You know, the way the edges are distributed and orientations and all those kinds of things. So the computer is able to look across these multiple features and find, well, what is making the images in that class different from the rest. So this is the application of that classifier. If I compare this to another one which we trained for nature scenes, well, it's also finding stuff that's green. But, you know, it's finding the matches on how this classifier was trained, and in this case they were more landscape scenes, and you know, maybe it's, you know, also color dominated, but there's something about the texture, the smoothness, the orientation, and so on. But you shouldn't get caught up on the names we put here, greenery, nature, and so on. I mean, this is just meant to illustrate how the system works, how it can be trained, and so on. Basically, you can train it however you want, and you can call your classes, you know, whatever you feel is best matched. I'll show some other examples. This is one that isn't perfect at all, but it shows the strength in the approach that we're taking. This is a person classifier, and it doesn't use face detection. It's not looking for portraits. It doesn't know about eyes and so on. It's just, again, saying, well, out of the examples that were trained for a person classifier, what are the characteristics? How things appear spatially, with texture, with smoothness, with color, and so on, that capture face scenes. And it's not perfect. This is the face of a dog, and this is some kind of window scene, and this is a statue. But for the most part, it's done a really good job at picking out from this data set across a diversity of how persons can appear in a video clip. One more I'll show here is this one, because this shows that spatial information is also important. This is just our blue sky classifier, and you know, it's doing a pretty good job at pulling out scenes with blue skies. And it's not just finding blue, it's not just finding the green, it's where they appear in the image spatially, and so on. So that's really a good illustration of how it works. I'm going to switch here to a different data set. This is a news data set, also we obtained from NIST as part of the, I'm sorry, yeah, question? Yeah.
All the things you mentioned in the beginning.
I'm sorry, I didn't hear. Are you asking, are we including sound?
Yeah, we trained on sound.
Okay. No, the example I showed previously is not using any sound or audio and so on. It's purely a visual. But everything I'm describing here on visual can be applied to audio as well. In other words, extract features, build models on top of those features, and create classifiers. And people have done this for things like speech versus music detection and so on. So that's also a rich area of work. Okay, another question? Yeah.
Yeah, so just now you have showed the people class. So do you use any spatial features? Some other for the nature, do you use any spatial features?
The question is, do we use for the face classifier or the others spatial features? Is that what you're asking? Spatial?
I mean, not just spatial. Yeah. Any feature different from this?
Oh, special. Okay. No, we don't. So in other words, we're very interested in scaling to thousands or tens of thousands or hundreds of thousands of classifiers. And we want to do this without requiring a PhD student for each one, because that's certainly one way you can approach the problem. So there's something to be said for trying to build on a common standard set of features, and we know these features are good. They've been, a lot of them have already been worked through the MPEG7 Standard body. Their performance has been measured. You're always going to find maybe new ideas, for how to capture information from images, but it's a pretty solid foundation that we're building on. Doesn't mean we'll be able to build a classifier for everything that's out there. I don't think so. But there's still a large portion of the semantic space that we can reach using the set of features that are here. Yes?
I may not be understanding quite right, but I think you train each word, and that it requires human interaction for each word, of which there's many words that somebody might type into a search. Does that mean you need, huge amounts of human interaction for this to train all the words?
So the question is, how much human interaction do you need for words and so on? Maybe I can hold this question for a minute, because just coming up in the talk, I'm going to talk about some efforts to build out the semantic space. But the idea is you don't train a model for each word. You may train a model for some visual category, and with that category you may associate a whole bunch of words later. So, there are a lot of ideas for using things like WordNet or using statistical techniques based on words and their relationships that will land you on a good set of categories for a query. So we'll come back to that one. But I do believe, though, there is some part of this which is maybe it is an endless problem to create classifiers. But you can certainly get started on some core sets, and I'll talk about some of the work to do that. Yeah.
Can you give us an idea of how big are the feature sets associated with a particular feature here? So do you work with 100 features, with 500, with 50?
What I'm showing here typically uses more than 10 descriptors, and it's a total of probably 5,000 dimensions. So, in other words, these vectors in the end, if you added them all together, we're talking in the order of 5,000 or so. And it's easy to find information about these things. So, if you can get a copy of MPEG7 specification, you can see, what does it take to describe a color histogram, an edge histogram, co-occurrence, texture, color parallelogram. All of these things are well documented.
Do you have any features that takes advantage that it's a video, not just one frame of image? Or do you run it on each frame of the image for the features and do sort of a statistical sum or something?
Yeah, the question is, what do we do to treat video as a video as a temporal medium as opposed to image frame. So actually I chose not to go into much detail on that one here today. So we have done some work on temporal, and we have publications on that topic as well. You can do a lot of things. You can run your classifiers on image frames and then look at trajectory in the semantic space, which can be very interesting. One example of that is, so I mentioned the one about airplane landing. Well, you have more sky in the beginning and more ground in the end. I mean, that kind of thing. So sometimes your image classifiers can be a good starting point for learning a temporal concept. Okay. So one more example here of search, and then I'll go back again. So this is a news data set. So the difference between this and the previous one is this one has a full speech transcript, which is searchable. This video comes from a number of sources, US, Chinese, Arabic, and so on. But somebody has done the work to get the speech portion out of all of this, which may have included language translation as well. All right, so let me just do a query here, and when I don't put any modifier in the string, it's just going to match against the speech transcript. So I've asked it to find those video clips that have basketball in the speech. And this is typical of what you get when you're relying on speech as for your video search. It doesn't give a good indicator what's visually being shown. So maybe an anchor person is introducing a next segment or something like that, but not very good. But what we can do, and I'm going to redo the query here. So the system is suggesting basketball classifier, and here the computer is finding which of the video clips score highly on that classifier. And the interesting thing here is when we relied on the computer's ability to detect what is likely basketball, not only did we increase the precision, so the results are very highly relevant in the top matches, we also increased the recall, because it's not obvious if you relied on the speech that these scenes would have easily have come up. Now, in some cases, there are words like NBA in there and the Knicks and those kinds of things. So maybe with some really smart processing of the text, you could get some of them. Let me show one more example where a lot of this information can come together for search. So I'm going to type a query here for weapons. And being a news corpus, there's often discussion on a topic like that. And again, we're relying solely on speech, and the user can kind of hunt through and say, well, which of the scenes that may be relevant, but you can also feed that back to the computer. So we can say, well, visually, this is showing something that looks weapons related. Here's another example. So let's just feed these back to the computer and really have a multimodal query. So now the query the system is going to answer is, give me the matches that say weapons in the speech and are like this image and like this image that the user has fed back. And so you can see right away, pretty quickly, in this pretty large news data set, we're getting pretty specific results for the user's query. And one more thing I'll just point out here is, so I'm not showing how the classifiers are really coming in to support this, but one of the ways which we can see is, out of the results coming back, the computer is analyzing those and saying, here are the classifiers or the categories that seem to be most relevant for your query. It's saying the scenes look like they're military related, or a lot of them are outdoors or showing crowds. So the system is giving the user the ability to say, yeah, well, give me just the ones that are military, that score highly on the military category. We can again feed that back to the system. So now we're looking in the speech, we're looking at matches based on certain examples, and we're taking into account the classifier for military, which is going to help rank them again. So you can see how all of that comes together in search. Okay, so let me back here. Okay, so I showed some examples of the search engine. So, what's behind the scenes here? We had a publication just a month ago at ACM Multimedia Conference. But the idea is to treat video queries as something different from an ordinary search, in that depending where the user is in the process, it can be more than just having a one-word term entered into a search box. But we can think of a query as having some text statement of information need, but also examples, either because they started with examples or as they're interacting with the system. So how to use all this information together, the text plus the examples, to do things which expand the text, expand the examples, expand into our classifiers to find out what is most relevant for the user's search, and then use that. And so anyway, I think I'll not go into a lot more of the details there. Just give a result here, and I know there's a lot of cryptic stuff on the slide. I just grabbed it right out of the paper. The important thing I wanted to show here is the difference between what's on the left and what's on the right. On the left, this is the performance we got in the retrieval system when we relied solely on text. That means text part of text statement for the query, text being matched on the back end, when we treated these queries as really multimodal queries. So they have a video portion, they use classifiers, we're matching based on visual content, we got a significant jump in performance. So that's saying you really should treat video as something different to get the best results. Okay, I think I'll skip this one here. Okay, so there was a question before about so how do we grow the number of classifiers and so on? And this is a really important question. A lot of papers and so on talk about this idea of bridging the semantic gap. That's what we're working on for video, which is going from features to semantics, and how to do that and how to make the machine learning work well and so on. But we need to make sure to not build the bridge to nowhere. In other words, just demonstrating that you can detect a sunset well may be neat, but really, is that what the user needs in the end for search? So it's important to develop these semantic spaces, and there are a number of dimensions that need to be considered to do that. And this also maps back to the ideas about wanting to have broad coverage. So sometimes you don't care about your domain of video. You just simply want to know, is a scene outdoors? Could be in a broadcast, it could be a consumer photo, it could be user-generated content. But in other cases, you want to go deeply. For example, within news, there are a lot of very specific concepts that are relevant there, or within topics in news like weather and disasters, or in sports scenes and so on. I'm going to talk about one effort on broadcast news in particular called LSCOM, and this was an effort over about a 2-year period, which wrapped up last year. There's actually a good paper on this in IEEE Multimedia last summer, but it brought together scientists, end users, and library science type people from news organizations, and through a series of workshops, they designed an ontology of 1,000 concepts that achieve a balance of being useful to support search of broadcast news video, but also technically feasible, that you could actually think that within a 5-year period, a computer could reasonably detect those kinds of things. This is available for download. Actually, it's being hosted now at Columbia University's site. It's got a bunch of things there: the ontology of 1,000 concepts, a fully annotated broadcast news data set for these concepts, and anyway, just some idea of the kinds of institutions and so on who have accessed this one. Maybe even more have downloaded it since I got this grab. But the overall process was an iterative thing. So in other words, started with some draft of concepts, and those were annotated, and we can see some kind of breakdown, how many were event activity types, 13%, how many were people-related, location-related, objects, scenes, programs. And then there was an effort to model those, see how well they perform, and feed that back. If something was hopeless and there was no projection that it could be done, then it was removed. If something wasn't useful, then it was also not considered. But this was an iterative process for a couple of years. One of the places that ontology has been used is in the TREC video retrieval benchmark. This is a yearly video retrieval evaluation organized by NIST. The workshop this year is in 2 weeks in Gaithersburg, Maryland, if anyone is interested in going to that. But what they do every year is they have a public evaluation. They make a large video data set available, and then they create some tasks around that, like automatic classification of contents, video search. You can see a number of the other ones here. And this one has been getting a lot more interest in participation. Well, there were 70 people last year, 70 participants, which means universities or research labs and so on. I'm not sure of the number this year. This is an extract from the LSCOM ontology that's part of that benchmark. So the participants are given a training data set which goes along with these categories. They train up their system. Then NIST gives a new video data set, and the participants have to run their classifiers against it and give the results back to NIST without looking at them. And NIST will then score and produce, retrieval plots and so on. The search task is a little bit different there. It's similar in that a data set is made available, people ingest it into their systems, and then NIST provides a set of retrieval tasks. And they can span the range from looking for specific individuals or different scene types. And all of these are multimodal in that not only is there a statement of information needed in the text, but they give example video clips and so on that go along with these categories. I wanted to mention one other here. Actually, let me see how I'm doing on time. Okay, I think I have time. Because you may enjoy this one. This was the first year this event was run. It's called Video Olympics. And we helped organize this one. We were also a participant. This was something out of University of Amsterdam.
Video is quickly becoming the most important information carrier of our time. YouTube and Juiced showed video is no longer the domain of broadcast television only. Video has become the medium of choice for many people communicating via internet. Despite its popularity, finding specific video footage in a large collection is a difficult scientific problem. Today we are at the Netherlands Institute for Sound and Vision, the Dutch Broadcast Video Archives. We are at the first Video Olympics, a showcase of several state-of-the-art video retrieval systems. The goal in video retrieval is to satisfy a visual information need. For example, find clips of flying helicopters. Based on this need, a user starts an interactive search with the video retrieval engine. To compare systems, benchmarks are designed in which research prototypes work on the same video datasets. The nice thing is that different systems allow for different strategies to collect as much correct results from the video data as possible. At the Video Olympics, we aim to make the possibilities and limitations of these systems tangible. The uniqueness of the Video Olympics is that we bring systems from the lab to the audience. We do so by having systems compete simultaneously on a common search task.
Find shots of US President George W. Bush Jr. walking.
All systems solve the search task on the same video archive within a 5-minute time frame.
Time is running and we're on the board. The first results are there. Go for it. almost as good, but they haven't found all those repetitions. Try not to cheat. Try not to cheat.
All retrieval results are communicated to the audience on a scoreboard in real time. Good results are awarded, bad results are penalized.
Those scores, they have crowds, but it's not insane.
It allows for on-the-spot comparison of the performance of different video search engines. But it also allows to evaluate their interfaces and ease of use.
Don't forget to vote for the system that you think is really the one you'd like to use.
The main aim of the Video Olympics is giving the audience a good perspective on the possibilities and limitations of current state-of-the-art video retrieval systems. In the spirit of the Olympic Games, participation is more important than winning. That is why all participants go home with a Golden Retriever Award. But of course, the real winner is the audience.
So we got one of these Golden Retriever Awards as well. It was really nice. Only if you noticed, the wine mixed with the event, I think only in Europe could you have such a thing. But it was certainly a nice touch. This will be organized again next year in Niagara Falls. So, certainly is an interesting activity. The last thing I wanted to just talk about here is MPEG7 Standard. This has really been designed to support video search and other forms of multimedia as well. What it does is it standardizes an XML schema, or basically a set of descriptors and description schemes for multimedia contents. And it includes descriptors at the low level, things like, well, how would you describe a color distribution, to higher level things at the semantic level, as well as other more typical things like production metadata, titles, creators, authors, and those kinds of things. What's interesting is when we put a lot of these together, not only the coding of the resources, but the XML, then there really are units of transaction that can be created, and this is where MPEG-21 comes in. But anyway, I won't go into MPEG-21 really today. But around MPEG-7, as I mentioned, it gives the ability to express in a standard representation the description of multimedia resources. So I think this is a good sampling of how approaches can come together to support video search. I just wanted to put a couple of links here. Our tool for our system is available for trying out on the IBM AlphaWorks site. You do need to log on and get an ID there, but it's easy to download. And just a link also to our website. So that concludes my talk, and I'd be happy to take any questions in the last couple of minutes. Thank you.